Hello everyone, let's go ahead and take a look at the vector form of a plane. Now we're going to use this setup here to go ahead and derive that vector form. And what we have is we have here the origin, the normal vector to the plane which is represented by this green line, and also the resultant vector, which is of course any vector that points to the plane and starts at the origin. Now we're also going to have theta, which is going to be the angle that is created by the normal and the resultant. And what I have here is called d, which is, of course, if we take a look at this diagram, the distance from the origin to the plane. Now, what we're going to say then is this capital D is the distance from the origin to the plane, and it is also known as a scalar projection of r onto n. Now, what exactly is a scalar projection? Now, remember that since we're dealing with a scalar projection, the actual value that we're going to be coming out with is a scalar value. And the reason why it's called a projection of r onto n is because imagine that we have a light that is shining straight down at the tip of this point of r. Then basically the shadow that is going to be cast, which is created by r onto n, is going to be this length called capital D. So that's what the scalar projection is. For us, it's going to be important that we recall and we remember that this is actually the distance from the plane to the origin. Now, it's very simple for us to go ahead and derive the vector form of a plane. Because we know that the cosine of theta is going to be this capital D divided by the magnitude of r. So the cosine of theta, capital D, divided by the magnitude of r. Now, if I go ahead and multiply both sides by the magnitude of r, I come up with the magnitude of r times by cosine theta is equal to this capital D. Now, what I'm going to do is I'm going to multiply both sides by the magnitude of the normal vector. And if I do that, notice that I come up with something that is very familiar here. That is actually going to be r dot n. So notice that r dot n is actually going to give us this magnitude of n times by d, which is just going to be a constant. Now, if we go ahead and multiply both sides by 1 over the magnitude of n, so notice 1 over the magnitude of n, in this side here, on the left-hand side of the equation, notice that what I'm going to come out with now is that I have r dot n hat, again, which is the unit vector of the normal vector, the unit vector form of the normal vector, is equaling, again, d. And so here is going to be a very important form for us, because if we want to go ahead and apply it to particular applications regarding the distance from the plane to the origin, then this is the form that we want to use. Of course, we could use this form, but it doesn't give us as much information. So, since we're going to be dealing with distances now, and let's go ahead and apply that then to two situations. One, we're going to go ahead and take a look at the distance between two planes. And then we're also going to go ahead and take a look at the distance between a plane and a point or a line. Now let's go ahead and just get an idea of what's happening now between the distance between two planes. Now what I have here is I have plane 1, plane 2, plane 1, plane 2, plane 1, plane 2. And of course we need to make sure that those planes are actually parallel to each other so that we can then go ahead and determine the distance between those two planes. Now, notice the difference between these diagrams is that in this particular case, the origin is below both of the two planes, or said another way, that both planes are above the origin. If that's the case, then generally speaking, what we're going to be able to say then is that the directed distance from the origin to the planes are both going to be positive. Now, in this particular case over here, notice the situation changes because the origin now is between both of the planes. And so therefore what we're going to say is that d sub 1 is going to be greater than 0 and d sub 2 is actually going to be less than 0. In this case over here, notice that both planes are below the origin and therefore the directed distances are both less than 0. Now if we wanted to go ahead and find the distance between the two planes, which is what we're trying to describe here, then for this particular situation it's going to be very simple. We just take d sub 1 minus d sub 2. In this case over here, it might be a little bit more confusing to see, but again, basically all we have to do is take d sub 1 minus d sub 2, right? Because if we do that, then the negative value would then become positive, and then we add the two distances, which is what we need to do in order to find the distance between both planes. Now in this case over here, what we need to do is we need to go ahead and take d sub 1 minus d sub 2. Okay, and what we can do then is we can actually go ahead and come up with a generalization. Now, I could write this as d sub 2 minus d sub 1 or d sub 1 minus d sub 2. It's really up to you. We'll go ahead, since we're being consistent with d sub 1 minus d sub 2, we'll say that. And we just need to make sure that that particular distance is going to be a positive value, and therefore we take the absolute value of the difference of the distances. So if we go ahead and have two planes, we can always go ahead and find the distance between the two planes by making sure that each one of the planes are written in this form, which will then give us the distance from the origin to that particular plane. Now, oftentimes what's going to happen is that you're not going to be given two planes. You're going to be given a plane and a point, or a plane and a line. Now, how do we go about using this particular idea and this particular result to help us go ahead and find that distance? Now, there's a lot of different ways that you could do this, but this is one way that I like to use. This is one particular method that I like to use because it uses this particular idea and this particular idea, and it's very efficient. Okay? Let's say, for example, that we have a plane 1, which is going to be 2x minus y plus 2z is equal to 1. And then we want to find that distance from the plane to this point, which is point A, which is at 1, 2, and 3. Now, if I go ahead and take a look at plane 1, very simple to go ahead and change that into our vector form of a plane, which is just going to be r dot 2, negative 1, 2 is equal to 1. Now notice that it's not yet in this particular form. Right now it's in this particular form. But anyway, we can still use it because the most important thing that we need to find at this point is the normal vector. So the normal vector for plane 1, right here, is going to be 2, negative 1, 2. Since we are going to embed, which is going to be the key word, we're going to embed point A in another plane so that we can have this situation, we need to actually go ahead and use the normal vector to be the exact same value. So what's going to happen then is that if I embed this embed this point into another plane that is parallel to plane 1, let's use a dotted line there, then basically, being that this is going to now be plane 2, which contains point A, I need to make sure that the normal is going to be exactly the same normal as plane 1 in order to ensure that both of these planes are now parallel to each other. So now I can create plane 2, because plane 2 has to contain point A, and it also has to have the same normal as plane 1, and so I can now go ahead and find my lowercase d. So I got 1, 2, 3, which is the point A, dot that with 2, negative 1, 2, which is the normal vector of 1, plane 1, and then I can come out with the value of d being 6. So what I have now is plane 2 is actually going to be r dot 2, 1, negative 1, 2 is equal to 6. Now again, remember the idea is that we need to get it into this form here. In order to do that, I need to find the magnitude of n. The magnitude of n, which is going to be the same for both the plane 1 and plane 2, I'm going to come up with the square root of 9, which is equal to 3. Therefore, what I can say then is that the distance between plane 1 and the point is the same thing as the distance between plane 1 and plane 2, which is a parallel plane containing point A, is going to be the same thing as the absolute value of d sub 2 minus d sub 1. Okay, I changed it there, but it doesn't matter, it's the same thing. It's going to come out to be numerically the same value. And what I come out with is going to be 6 over 3, because remember that this is 6. I need to take that and divide it by 3, minus 1 over 3, and that of course is going to be 5/3. Okay, so let's kind of wrap things up again. The vector form of a plane is going to be based upon this value of d, which is the distance from the plane to the origin, and the scalar projection of r onto n. Using that information, we can then go ahead and come out with this very nice form, the vector form of a plane, which also tells us the distance from the origin to the plane. If we go ahead and think of two different planes then what we can do is we can actually go ahead and determine the distance between those two planes by using this initial statement or this formula. And then after that, regardless of whether we're dealing with a plane and a point or a line, if we embed that point or plane into a parallel plane, if we embed that point or line into a parallel plane, then what we can do is we can use this particular initial statement or formula to then go ahead and very simply find the distance between those two three-dimensional geometric objects. So let's go ahead and see how you guys do, and hopefully that gives you a much clearer idea of the derivation of the vector form of a plane. So see you in class, and we'll take some questions during that time. See you later. Bye-bye.